Have you ever heard someone make a point and you just think, that sounds right, but is it actually right? Well, today, you and I are going to become logical detectives. We're going to crack the code on arguments, figuring out how to tell the solid, airtight ones from the fakes that just sound good. All right, let's jump in. So here's our first case file. You read this, and on the surface, it seems to make sense, doesn't it? It's got a nice, familiar flow. We've got two statements, what we call premises, and they lead us to a neat conclusion. But is the logic holding it all together really as strong as it seems? That right there is the million-dollar question. And to figure it out, we can't just rely on a gut feeling. Nope, we need a proper toolkit. We have to look at the very blueprint of the argument itself. So let's get our gear together and learn the basics. Okay, so the most important tool in any logical detective's bag is what's called a conditional statement. You probably know it better as an if-then statement. This little guy is the absolute bedrock of logical reasoning. If we can get a handle on this, we're well on our way to solving our case. So here's what it looks like in the wild. We've got an if part, which we'll just call P, and a then part, which we'll call Q. Pretty simple. If P happens, then Q follows. For instance, P could be n is a factor of 8, and Q could be n is a multiple of 2 or negative 2. If that first part is true, the second part has to be true. Makes sense, right? But this is where things start to get really interesting. So once you have a basic if P, then Q statement, you can actually rearrange it in three very specific ways. These are known as the converse, the inverse, and the contrapositive. Now, understanding these three twists is absolutely critical because, and this is a big one, they are not all logically the same. Let's break them down. All right, let's check out these first two twists. The converse, over on the left, is super simple. It just flips P and Q. So it becomes if Q, then P. The inverse on the right keeps them in the same order, but it negates both of them. So if not P, then not Q. Now, a little warning for all you detectives out there. Just because the original statement is true, that does not automatically mean the converse or the inverse is true. They can be really deceptive. And that brings us to our superstar, the contrapositive. This one does two things. It flips the order and it negates both parts. So it becomes if not Q, then not P. And here is the whole point. The contrapositive is the only one of these three that is always, and I mean always, logically the same as the original statement. If the original is true, the contrapositive is true. If it's false, the contrapositive is false. It's like a rock-solid logical twin. All right, we have our toolkit. We get if-then statements. We know about their different twists. It's time to put these skills to the test. Let's open up our first official case file. Okay, here's the argument. That first sentence, all freshmen must take a writing course, is just a fancy way of saying, if a student is a freshman, then they must take a writing course. The next part tells us, Caroline is a freshman. And the conclusion? Therefore, Caroline must take a writing course. So let's put it on the analysis board. And the verdict is valid. This is a classic textbook example of a solid argument. It's a form called modus ponens, and the structure is perfect. If P, then Q. We're told P is true, therefore we can absolutely conclude that Q is true. This structure is always logically sound. Case closed. Okay, so now that we've seen what a real valid argument looks like, let's go back to our very first mystery, the one about Keisha and the apple. Armed with our new tools, we can see it for what it truly is. It is time to unmask a very common imposter. Let's look at the evidence again. First, we translate that first sentence into our if-then structure. If a person is healthy, that's our P. Then they eat an apple a day, that's our Q. The next sentence says, Keisha eats an apple a day. So that's confirming Q. And the conclusion is, Keisha is a healthy person, which is P. You see the pattern there? So the verdict is invalid. This is a classic logical mistake, a fallacy called the converse error. The argument sets up if P, then Q, but then it confirms Q and tries to work backwards to prove P. But it doesn't work that way. Just because all healthy people eat apples doesn't mean that only healthy people do. Maybe Keisha just really likes apples. And this, right here, shows you the difference perfectly. Just look at them side by side. Modus ponens, the real deal on the left, confirms the if part to prove the then part. But the converse error, the imposter on the right, confirms the then part and tries to sneak backwards to prove the if part. It's such a tiny, subtle switch, but it makes all the difference between solid logic and a logical trap. All right, detective, on to case file number 3. Now, this one's from graph theory, but don't worry, the logic works exactly the same. Our P is a graph has no edges. Our Q is it has a vertex of degree 0. So if P, then Q. Now, the second statement says this graph has at least one edge, which is just another way of saying not P. And the conclusion? The graph does not have a vertex of degree 0, which is not Q. The verdict is in, and it is invalid. This is another one of those common fakes, and this one's called the inverse error. Remember the inverse we talked about earlier? This argument uses that same flawed logic. It says if P then Q, then it tells you P is false, and from that it tries to conclude that Q must also be false. But the original statement never said anything about what happens if P isn't true. So this is another imposter argument. Okay, let's get to our final case. Now, I know this one looks a little intimidating with the algebra, but don't let it fool you. The underlying logic is exactly what we've been looking for. Let's just break it down piece by piece. Let's crack this thing. Okay, first up, P is the product of two numbers is 0. Easy enough. Q is at least one of the numbers is 0. So our rule is if P, then Q. Now, the second piece of evidence tells us that neither number is 0. Well, that's the exact opposite of Q, so we have not Q. And the conclusion? The product is not 0, which is not P. So the argument structure is, if P, then Q, and we know not Q, so what does that mean for our verdict? And therefore, the verdict is valid. This powerful and totally correct way of reasoning is called modus tollens. It's actually the logical twin of our old friend, the contrapositive. It basically says, look, if P always leads to Q, and we can see that Q did not happen, then there's no way P could have happened either. It is a completely sound way to reason. Case closed. So what's the big takeaway from our investigation today? We've seen that some arguments that, they sound pretty good on the surface, are actually built on faulty logic, while others are as solid as a rock. Let's put everything we found into a final summary. Here it is, your brand new detective's field guide to logic. On one side, you've got your trustworthy clues, the valid forms, modus ponens and modus tollens. You can always rely on them. And on the other side, you've got the deceptive imposters to watch out for, the converse error and the inverse error. They look close, but they will lead you down the wrong path every single time. It's all about checking the structure, not just how it sounds. So we've given you the basic tools of a logical detective. You can now break down an argument, see what makes it tick, and decide if it's the real deal or just a clever fake. So here's a final thought for you. As you go through the rest of your day, listening to people talk, scrolling through your feed, how many of these arguments, both the good and the bad, are you going to start seeing everywhere? Your detective work has only just begun.